So let's say we're pumping air into a balloon. As we do that, both the volume and the radius of the balloon will be changing, and the rates that they're changing are related to one another. And the reason being, the volume formula has the radius in it. However, it's much easier to measure the increase of the volume than it is the increase of the radius. Our new section is called related rates. And as we said, they are rates that are related to one another. We'll compute the rate of change for one quantity in terms of another quantity that it's related to. In a related rates problem, what we're basically doing is we're trying to find the rate of change of one quantity. Maybe it's a volume, maybe it's the rate of change of a radius or of a height in terms of another quantity. And that other one, it might be easier to solve for. The way we do this is we find an equation that somehow relates the two things. So maybe it's a volume formula, maybe it's a surface area formula, something like that. And then we use chain rule to differentiate both sides with respect to time. That's what's new about this here. All of our derivatives in related rates problems, because the time is changing and causing the different dimensions in our situation to change, we'll take our derivative with respect to time. Time will be our independent variable. We've seen so far the notation dy dx, meaning the derivative of y with respect to x. Well, what we'll see now with these is we'll see them with respect to t. So maybe we'll be working with a volume. Well, when we take the derivative, it'll be dv dt. If there's, say, an x in our problem, when we take the derivative, it'll be a dx dt. So basically, t is going to be our independent variable, but it won't be present in the problems at all. So therefore, it's kind of like you can think of it as we have like a v prime or an x prime. That's what dv dt, dx dt. Maybe if we have a radius sometime, we would then have dr dt. So we'll express it as the dt's, or you could do it as primes. But if you do it as primes, you got to keep in mind that your primes are with respect to time as we're taking these derivatives. So we've got air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So first off, I think it's important to identify what is it we're looking to find in the question. We want to know how fast the radius is increasing, so that's the rate that the radius is changing at. So what we're really looking for is we're looking for a dr dt. We're looking for the rate that the radius changes with respect to time. Well, we're talking radius, we've talked volume in the question, they've given us volume, so we need something that relates those things. We can use our volume of a sphere formula. V equals 4/3 pi r cubed. And then the questions will almost always give you some information at a given instant. So we'll list this as known at instant. Well, there, we want to find when the diameter is 50 at that instant. Well, when the diameter is 50, we know our radius then is 25. Now, the things you're finding at an instant, those do not get subbed in until after you've taken a derivative. The only things that can get subbed in before you take a derivative is anything that is constant throughout the entire scenario. Well, our only variables in our equation are volume and radius. Throughout our scenario, as the balloon is growing, both the volume and the radius are changing. So we actually don't have any things that are constant in terms of the v and the r. Okay, you could say the 4/3 pi is constant, and that's why that's already in the formula. So we will now take the derivative. And now when we take the derivative, remember it will be with respect to t. Think of t as your independent variable. So the v and the r, we think of them like y's when we do a derivative of a y. We have to do times a y prime. You could also write the y prime as dy dx. Well, in this case, we're doing dt's. So the derivative of v will be 1 times dv dt equals The 3 will come out front. 3 times 4/3 is 4 pi r to the second times dr dt. Okay, so that's like saying a v prime for the dv dt and r prime for dr dt. Okay, think of them like y's because our independent variable is t now. Well, dv dt, that is the rate at which the volume is changing. And we're looking for dr dt. So because we're looking for dr dt, we should be able to sub in for everything in the problem except for dr dt. Well, they told us dv dt was 100. So I'm just going to put this in as 100 because it's 1 times that. Equals 4 pi. Our radius is our radius at an instant. Well, we know that that's 25. So we can plug 25 in there. And then we have dr dt, which we won't plug in for because that's what we want to try and solve for. Now all we got to do is we need to get dr dt by itself, and that'll tell us how our radius is changing at that instant. So we'll have 100 equals 25 squared times 4 will give us 2,500 pi times dr dt. We'll divide our 2,500 pi over, and we'll end up getting 1 over 25 pi when that reduces, and that is our dr dt. Now our units, our volume was in centimeters cubed per second, so radius is a one-dimensional unit, so this should be centimeters per second that we are working with. And if you punch that in, that would be roughly 0.0127 centimeters per second. And what we just found is at an instant, at the instant the radius is 25, we found the rate that it was changing at. Okay, the rate of change of the radius. All right, next up, we have a water tank that has a shape of an inverted circular cone, like the one pictured, with a base radius 2 meters and height 4 meters. If water is being pumped into the tank at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 meters deep. So we want to find how the height is changing. So in this question, we are looking for dh dt. So it's important to identify that because eventually when we set up our equation, that is the only one we will not sub in for. Well, sometimes our units can help you. We've got meters cubed per minute. That is a rate of a volume because it's a volume rate over a time. So we're probably going to want to deal with our volume formula for a cone. Volume of a cone is 1/3 pi r squared times h. When we go to take the derivative, we can only have one variable within a term. So by term, we mean stuff that's being multiplied together. In the term on the right, that's a single term because everything's being multiplied. We currently have 2 variables. Therefore, one of the variables is going to have to be replaced. What we can do is we can use the geometric relationships in our picture to help replace one of those variables. And what we have here are similar triangles. Our blue section there has a radius of r and a height of h. The big triangle that it's similar to has a radius of 2 and a height of 4. So we can just set up similar triangles. The 2 corresponds to the r, as the 4 corresponds to the h. So this will give us 2h equals 4r. And because we want to find dh dt, it makes most sense to keep the h in our problem, meaning we want to substitute in for the r. So we'll divide both sides by 4 to get r by itself, and it'll give us h over 2 is equal to r. We'll now sub in. We've got our volume is equal to 1/3 pi h over 2 squared times h. Now, we have just one variable for each term, which is what we wanted. But don't rush to take your derivative. It'll make your life much, much easier if you first simplify as much as you can. So we'll have v equals 1/3 pi times h squared over 4 times h. Well, that's v equals, let's bring that 4 in the denominator out with the 1/3, so this will be 1/12 pi h cubed. Now this is nice and simplified. It's something that should be a lot easier to take the derivative of. We'll go ahead and take our derivative. Derivative of v will be dv dt. It's up to you if you want to put the 1 out front. 3 times 1/12 pi will give us 1/4 pi. Will now be h squared, and we've got to do times a dh dt. So because we were looking for dh dt in the problem, we should be able to sub in for everything except for that. dv dt needs to be a rate involving the volume. Well, if we go back up to the top, they said we're changing at 2 meters cubed per minute. So that's our dv dt. We've got 1/4 pi. We wanted to find at the instant that the height of the water was 3 meters deep. So that'll go in for our h. And then dh dt, that's the one we want to leave. So now we just have to work to get dh dt by itself. 3 squared is 9, so that'll give us 9/4 pi. Or you can think of it as 9 pi over 4 if you want. dh dt. Dividing by 9 pi over 4 is like multiplying by 4 over 9 pi, so that'll give us 8 over 9 pi equal to dh dt. And again, or you can think of it as multiplying both sides by 4 to get rid of the 4 to give us 8, and then dividing both sides by 9 pi. Now your height is a one-dimensional measurement. We were working with meters, and we had minutes as our time rate, so this is meters per minute. And if you punch that in your calculator, it would be roughly 0.283 meters per minute. So again, just to review what we did, we wrote a formula that represented our scenario. In each term, we only want a single variable. So in the term on the right, we had an r and an h, so we needed to somehow get rid of one of them. We wanted to keep the h because we were looking for dh dt. So we set up similar triangle proportion to sub in for the r. We were then able to take the derivative after we simplified, plugged in for everything except for the dh dt to find our rate for our height. Next example, a ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So, we basically have a right triangle here, where the hypotenuse is the ladder. You've got the vertical height, and you've got the horizontal height where it's sliding away from the wall. Something that we know is constant is the ladder is always 10. So we can go ahead and put that in our picture right now because that is not changing at all. Now we need to pick some variables for other parts. Maybe let's call them x and call them y. We want to know how fast is the top of the ladder sliding down the wall. Well, that would be dx dt because we want to know at which length x is changing. Okay, and I just picked x randomly as a variable there and y is the base. You could pick any variables. So the relationship we can set up is that x squared plus y squared is equal to 10 squared. Again, the reason we could put the 10 in is because the 10 is constant throughout the scenario. The 6 is what we're finding at an instant. That's not staying at 6 the whole time. Each term can only have one variable. Well, x squared is a separate term from y squared. They're being added. Okay, a term is all stuff that's being multiplied together. So therefore, we can go ahead and we can take the derivative. Derivative of x squared will be 2x times dx dt. Plus derivative of y is 2y times dy dt. 10 squared is 100. Derivative of 100 is just 0 because it's a constant. So we're looking for dx dt. So we should be able to sub in for x, for y, and for dy dt. Well, dy dt is the rate it's sliding away from the wall, which they told us was 1. The bottom of the ladder, we want to know when it's 6 feet from the wall. Well, that's our y value at that instant. We're trying to find the x dt. So we should be able to find x. Now, they might not always come right out and say everything in the problem, but because we're finding when this is 6, we can do Pythagorean theorem, or you might just recognize the triangle. X squared plus 6 squared equals 10 squared. That's x squared plus 36 equals 100. X squared is 64, so x is really 8. Basically what this is saying is, because the ladder's always 10, at the instant when y is 6, x must be 8 at that instant. So we can go ahead and plug that in. Now we just have to work to get dx dt by itself. This will be 16 times dx dt plus 12 equals 0. That's 16 dx dt equals negative 12. And when you divide the 16 over, dx dt would equal negative 3/4 or 0.75. Now that was a one-dimensional measurement. It was in feet, so we were doing feet per second. The reason it is negative is because the length is shrinking. X is getting smaller as the base of the ladder is being pulled out. We'll see in some other problems that they give us the rate as a positive, and it's up to you to recognize that that length is actually shrinking, and we'll have to put it into the equation as a negative. So we will see that on some other problems. So to review, first read the problem carefully. If they don't give you a diagram, try and draw some diagram. If you have to pick variables for certain quantities, go ahead and do that. And also, if anything's constant the entire time, label those as constants in your picture. Decide what rate you're trying to find. And if you're given any other rates, you can list those as like a dv dt or dy dt or whatever. Write some equation that represents the quantities. Each term can only have one variable in it. So like when we had the height and the radius, we had to figure out a way to get rid of one of them and sub in for it. Take your derivative using the chain rule. What we mean by chain rule is you'll have your variable over dt, d your variable over dt each time. And then you should be able to sub in for everything except for the thing you're looking for, and then just get that by itself. That's all for today's video. We'll see you next class period.